Result, the equation of the circle with the x1 y1 and x2 y2 as extremities of one of the diameters of the circle is x minus x1 into x minus x2 plus y minus y1 into y minus y2 equal to 0. Let a x1 y1 and b x2 y2 be the two extremities of the diameter AB of the circle. So this is a x1 y1, this is b x2 y2. So two end point of the diameter. Let p x comma y be any point on the circle. So consider the point p x comma y. Now join AP and BP. So joining AP and BP. So we know the angle in a semicircle is 90 degree. So the angle APB is equal to 90 degree. So the line AP is perpendicular to BP, right? The angle between the lines AP and BP is 90 degree. We know that if two lines are mutually perpendicular, then the product of their slope is -1. So slope of AP into slope of BP is equal to -1. This is equation number 1. Now we are going to find the slope of AP, slope of AP and slope of BP separately. So we know the 2-point form. We are using the 2-point form to find the slopes. If line joining, the slope of the line joining x1 y1 and x2 y2 is y2 minus y1 by x2 minus x1. So to find the slope of AP, right? So slope of AP is equal to y minus y1 by x minus x1. That is equation number 2. To find the slope of BP is equal to same. We are using the same formula, y minus y2 by x minus x2. That is equation number 3. From 1 to 3, the product of slope is -1. Therefore y minus y1 into y minus y2 by x minus x1 into x minus x2 is equal to -1. Just to do the cross multiplication, y minus y1 into y minus y2, which is equal to minus x minus x1 into x minus x2. So this implies y minus y1 into y minus y2 plus x minus x1 into x minus x2 equal to 0, which is to be proved. Next result, the position of the point p x1 y1 with respect to a circle x square plus y square plus 2gx plus 2fy plus 2 plus c equal to 0 is actually the point in a plane containing the circle is outside or on or inside the circle according as x1 square plus y1 square plus 2gx1 plus 2fy1, not y2, y1 plus c is greater than 0 or equal to 0 or less than 0. Suppose if you are having a point on the plane and a circle, right? So we are checking whether the point is outside the circle or inside the circle or on the circle. Just to put the point values. Suppose the point is x1 y1, then put x is equal to x1 and y is equal to y1 on the circle. If the value, if you are getting a number, right, the value is positive, that is greater than 0, that point is outside the circle. Suppose the value equal to 0, the point is on the circle. The value is negative or less than 0, then the point is inside the circle. That is what the result is telling, right? We are going to see the proof. Given equation of the circle x square plus y square plus 2gx plus 2fy plus c equal to 0. We know the center minus g minus f and radius r is equal to root of g square plus f square minus c. So given plane, a circle, then center of the circle, let p x1 y1 be any point on the plane, right? So join CP. So the point of intersection of the line CP and the circle, given circle, is Q, right? Let it be Q. So CQ is nothing but radius. Clearly radius is root of g square plus f square minus c. Suppose the point lying outside the circle, right? So in this case the distance CP is greater than the distance CQ, right? Clearly the distance CP is more than the length CQ, right? So CP square is greater than CQ square using the distance formula, CP distance. So we know x2 minus root of x2 minus x1 the whole square plus y2 minus y1 the whole square, right? So CP square, that means x1 minus g the whole square plus y1 minus f the whole square within the square root, right? The whole square greater than r square. So r we know root of g square plus f square minus c, substituting those values and using a plus b whole square formula. So x1 square plus g square plus 2g x1 plus y1 square plus f square plus 2f y1 greater than g square plus f square minus c. So x1 square plus g square plus 2g x1 plus y1 square plus f square plus 2f y1 minus g square minus f square plus c is greater than 0. This implies x1 square plus y1 square plus 2g x1 plus 2f y1 plus c is greater than 0, which is to be proved. This is the first result. We are going to second result. Suppose the point lying on the circle. Then what is the distance? Suppose P is coincide with Q. Then the distance CP and CQ are same, equal, correct? So the distance CP is equal to CQ. So this is the case, right? Q and P are coincide. Both distances are equal. So CP square is equal to CQ square. We are using the distance formula. Then we are using the same idea. So x1 square plus g square plus 2g x1 plus y1 square plus f square plus 2f y1, which is equal to g square plus f square minus c. So finally, because g square minus g square, f square minus f square get cancelled. So remaining you will get x1 square plus y1 square plus 2g x1 plus 2f y1 plus c equal to 0, which is to be proved. This is the second result. Suppose the point lying inside the circle. P is inside means the distance CQ is more than CP, correct? So the distance CQ is more than CP. So this is the case. If it is the case, then CQ, the length CQ is more than length CP. So CQ square is greater than CP square, right? So the change the inequality there. That is mod CP less than mod CQ, right? Small typo error is there, right? So CP square is less than CQ square. So using the same distance formula, so you will get x1 plus g the whole square plus y1 plus f the whole square less than g square plus f square minus c. So x1 square plus g square plus 2g x1 plus y1 square plus f square plus f 2f f1 is less than, is not equal to, less than g square plus f square minus c. So x1 square plus g square plus 2g x1 plus y1 square plus f square plus 2f y1 minus g square minus f square plus c is less than 0. So finally you will get the result x1 square plus y1 square plus 2g x1 plus 2f y1 plus c is less than 0. In the previous step, that is second step, less than, yeah, that is correct. So finally which is to be proved, that third result also proved. Thanks.